The topic of periodic functions is a very important one for engineering and the sciences because it tells us how to deal with functions that repeat themselves in some way. So you can think of lots of different examples of that. For example, how much solar energy we're getting in the day-night cycle, increasing and decreasing. We can think about a rotor going around. We can think about other cyclical patterns like an AC signal on an electrical grid. So we are going to have to introduce a couple of topics in this lecture that allow us to deal with periodic functions. And then in the next couple of lectures, we're going to analyze those functions in terms of their different frequencies using a Fourier series. So the first thing we need to do is to define what we mean by the period of a function and what is a periodic function. Very simply, we're going to define it as a function that when I shift it over by a certain amount t, I get the same function back again. So again, if I take a function and I shift it over, I get the same function back again. That's going to be a periodic function. We're going to define the period of the function as being the shortest amount I have to shift it over by to get my function back. Now, you notice that I say the shortest amount I have to shift it over by. You can think about the day-night cycle. I could shift the day-night cycle over by a day, 24 hours, and get the same cycle of light and dark again. But I could also shift the day-night cycle over by 2 days, 48 hours, and get the same pattern of night and day again. The period is not going to be 48 hours. The period is going to be 24 hours, which is the shortest time I have to shift it over by. So let's see what that looks like mathematically. So we're going to say that a function is periodic if my function can be expressed in the following way. F of x plus t is equal to f of x for all values of x. That is, if I shift x by an amount big T, I get back my same function. And that's true no matter where I put x. So that's our definition of a periodic function. And we say that it has a period t if t is the smallest number I can put in here so that this is true. So let's take a look at some examples of functions which are periodic and try and figure out what their period is. Let's start off with example 1 here. So this function sine of x, we know that that's a periodic function. It's obviously just going between -1 and 1, bouncing back and forth, so it's repeating itself. But what is the period of this function? That is, what is the smallest value that I could add to x to get my function back again? So let's write sine of x plus big T is equal to sine of x. So I'm just stating that f of x plus t is equal to f of x. That's our definition of a periodic function. So what is the smallest value of big T that I can put in there? Well, have a think about sine of x and what it represents. As we're moving around the circle, sine goes from 0 to 1 to 0 to -1 and back to 0 again. And it achieves 0 back to 0 again when I've gone all the way around the circle. So clearly this is a function that is periodic in 360 degrees, or 2 pi radians. So we say that t is equal to 2 pi. Again, if I was to go around 2 times the circle, 4 pi, I would again repeat myself, but that's not the shortest time I have to move before I repeat myself. Let's take a look at another example, example 2. We've got here a function 4 cosine 7x. So what we're going to ask is, what is the value of t such that 4 cosine of 7x is equal to 4 cosine of 7 times x plus t? Now notice there that I shifted x, I just replaced it by x plus t. I didn't just add t in here. I had to shift x by x plus t. And so that 7 is also multiplying the t. So I get that's equal to 4 times cosine of 7x plus 7t. So what's the value of t that's going to give me back my function again? Well, cosine is just like sine. It's going to repeat itself every 2 pi. So what that's saying to me is that 7x plus 7t is going to be 7x plus 2 pi, because I know that cosine of 7x plus 2 pi is going to be cosine of 7x. So 7t has to be 2 pi, which gives me t is equal to 2 pi divided by 7. What about example 3? This is the function f of x is equal to x squared. Again, I want to find a value of t such that if I replace x with x plus t, this is true, these two expressions are the same, no matter what the value of x is. So while there might be some values of x for which this is true, this expression here is not going to be true for every value of x. So this is not a periodic function. And of course, a function x squared is not going to repeat itself. Another way to say that would be the only period here that would work is t is equal to 0. So this is not a periodic function. The last example we have is the graph here. So let's take a look at this graph and try and figure out what the period of it is. You can see that it's clearly a repeating function, but how often is it repeating? Well, the way that we can figure that out is just by picking any particular value of this function and moving across in the x direction to try and figure out where does that value come back again. So for example, the value of my function right here, if I shift over, I see the value reappears at that point. How far have I moved over? Well, this is actually 2 units, so t is equal to 2. And this is going to work no matter where I am on the function, so I could do it back down here as well. This value here at t is equal to 0 occurs at t is equal to 2. So big T is equal to 2, and likewise down here, if I shift over by 2, I get my function back. So that's the point about periodicity. It's not that we can just shift over to get the same value. It's that if we shift over, we get the same function, no matter what the value of x is. Okay, so let's see if we have a function defined in the following way, that it is indeed periodic. You see I've got f of t is equal to t squared between 0 and 3, and then outside of those values 0 to 3, it's equal to f of t plus 3. And that's a shorthand notation that I'm going to use to indicate that this is a periodic function with period 3. So what we're going to do to sketch this is let's save my little axis here for later. To sketch this, we're going to start off by looking at what happens between 0 and 3. So the bit we're given at the beginning. And we're told that that's equal to t squared between 0 and 3. So that's a function, it's increasing something like that. And we're told that we're including this point and we're not including that point. Okay, so that tells me what happens between 0 and 3. The rest of my expression here tells me that I just take that expression here and I shift it over by 3. That's going to tell me what happens between 0 and 6. It just repeats itself again. If you like, what I'm doing here is I'm copying and I'm pasting again my original tile. Let's do the same to the left. If I shift over by 3, I could also shift back by 3. I'm free to shift in any direction I like, because this is, after all, a repeating function. That gives me the value of the function between minus 3 and 0, and I can find the value between minus 6 and minus 3 by shifting to the left by 3 again. So you can see that this term here, f of t is equal to f of t plus 3, is basically telling me that I'm free to shift this over by units of 3 as many times as I like, because I can shift by 3, I can shift by 6, I can shift by 9, and so on. And so I've ended up here with a function which is indeed periodic, and it's also got these discontinuities, but the definition of my function has dealt with the values of that function at the discontinuity. So I'm including this point, but I'm not including this point. And this thing, of course, will go on forever. It's useful here to also indicate what our original function was. So our original function, if you like, the original little tile that I copied and pasted over and over again, was this little bit here. And you can see that the period of this is the width of that original tile, which is big T is equal to 3. Okay, so we can actually use this idea to calculate what the value of the function is at a value outside of that original tile, that original interval, 0 to 3, by writing f of 11 is equal to a shift of 3 plus a shift of 3 plus a shift of 3 plus a shift of 2. So I've got 11 written as 1, 2, 3 shifts of 3 plus a shift of 2. Now each of those shifts of 3 basically brings me back to where I began. If I was here and I shifted over by 3, I wouldn't change the value of my function. Again, I wouldn't change the value of my function, and I wouldn't change the value of my function. So each of those shifts of 3 gives no change to my value of my function. The only thing that actually matters is the thing that's left over, f of 2. Now that value, 2, lies between 0 and 3, which is the original interval that I had. So I can use the original function, which was t squared between x is equal to 0 and x is equal to 3. So I've got 2 squared, which is equal to 4. Now, we're going to concentrate on specific kinds of functions and periodic functions known as odd and even functions. These terms tell us something about the symmetry of the function when I swap it about the y-axis or I swap it about the x-axis. So let's see what I mean by that and start off with the definition of an even function. So an even function is defined in the following way. If my function has the property that when I take everywhere that I see x and I replace it with minus x, it doesn't change my function. So I change the sign of x, but I don't affect my function. Let's see an example of an even function. I'm going to choose the function cosine of x. So f of x is equal to cosine of x. If I change the sign of x, I've got the cosine of minus x, but the cosine of minus x is just cos x, which is my original function. So changing the sign of x doesn't affect my original function. Let's see what that would look like in a sketch. So again, what I'm going to do is I'm going to sketch my function cosine of x. That's my sort of typical example of an even function. So cosine does something like this. It's obviously a periodic function. And it's repeating itself every 2 pi units. Okay, so we notice here that if I was to take my function cosine of x and replace x everywhere with minus x, what does that actually mean? Well, replacing x with minus x means that my whole function here is just going to be like a mirror image. It's going to flip left to right. So I'm going to represent that as an arrow here. This means that x is going to be replaced with minus x. So you can see that if I was to flip my whole function around, I actually get the same function. This thing already is a mirror symmetric object. If I swap left to right, I get the same function. So cosine of x is an even function because it's symmetric when I swap left-right. Symmetric under a swap, left to right, and vice versa. So that's an even function. Let's see what an odd function would look like. So first of all, I'll define it. I'll give you an example and I'll sketch it. So the definition of an odd function is a function f of x that has the property that when I swap the sign of x, that is, I replace x everywhere with minus x, I get my function back, but with a minus sign in front. So I swap the sign of x, and that ends up swapping the sign of my function. So an example of that would be f of x is equal to sine of x. This is the typical odd function. So if I set x to minus x in sine of x, I get the sine of minus x, which is minus sine of x. It's minus my original function. So this is an odd function. Let's see what that would look like. Okay, so I'm sketching sine of x. Again, that's a function with a periodicity of 2 pi. It increases like that, and then it goes down like that, and it repeats itself, and it goes this way. There we go. So we've got pi, 2 pi, minus pi, and minus 2 pi. So this is a function with a periodicity of 2 pi. And let's see what we mean by that this is an odd function. So again, by swapping x to minus x, what I'm doing is I'm swapping this whole thing left to right. And we saw that an odd function is defined so that when I swap left to right, I get minus of my function. But minus of my function is like swapping up down. So f goes to minus f is a swap up down. So what we have here is that an odd function should be symmetric under a flip left to right and up to down. I have to do both flips to get my function back. And indeed, that's exactly what you see here. When I flip left to right, this up part here is going to be up here. So that's got the wrong sign, so I have to flip down again, and I get my function back. Likewise, this piece over here, when I flip left to right, is now going to be minus 1 over here. So I need to flip up down to get the correct value. So an odd function is equivalent to being symmetric when we swap left to right and vice versa, and up to down. So we've got to do both a left-right swap and an up-down swap to get an odd function. Now, it's the definitions here are a useful way to check whether or not your function is odd or even, and that should certainly be the first thing that you do. Now, not every function is going to be odd or even. In fact, there'll be lots of functions that will be neither odd nor even. That is, if I swap the value of x to minus x, then I don't get back my function, and I don't get back minus my function. So let's see some examples of that. So take a look at each of these figures and try and figure out whether or not these functions are odd or even or neither. So thinking about an even function, that means that when I swap left to right, I get the same function again. And an odd function is one which I swap left to right and I swap upside down. So looking at this function here, we see that if I swap left to right, I'm not going to get the same function back, because I'm going to get a function that's going to look something like this. Right, so swapping left to right is not enough. I also need to swap up, down, and that will actually give me back my function again. So this is two swaps, left and right, and up and down, so this will be an odd function. What about this function here? You see that if I swap left to right, I do indeed get my function back, so this is an even function. Let's take a look at this one here. Well, there's not really much I can do with this function. I can swap left to right, I can swap up and down, but I'm never going to get my function back, so this is neither. Last example. We see here we've got a periodic function, and if I was to swap left to right, what would this thing look like? Well, swapping left to right would mean that this value would go over here, this value would go here, and so on. So these lines would look something like that. So clearly these values are not the same. I have to do another swap up, down. So I need to swap left and right and up and down. So this is going to be an odd function. Now there's a couple of different useful properties that we can use for odd and even functions. And they're given at the very beginning of your notes here. So we have that from the definition, we have that an odd function is one that if I change the sign of x, I change the sign of f. And an even function is one which if I change the sign of x, I don't change the sign of f. But it can also form products and addition and subtraction of different odd and even functions. And each of these can be proven from these two definitions. So an odd function times an odd function is an even function. How might we prove that? Well, if I change the sign of x, then this becomes minus, and this becomes minus, and minus times minus is plus, so I get plus times my function, so it's an even function. Likewise, if I change the sign of x, I change the sign of the odd function, but not the even function, so I get minus sign here, so this is going to be an odd function. I can also add and subtract odd functions and even functions to get odd functions and even functions which are neither odd nor even. So let's use these ideas now to check the symmetry, whether it's odd or even, of a couple of different functions, and then prove that using our definitions. So cosine 3x, this is going to be an odd function, an even function. Cosine is even. So that's just an even function. The factor of 3 there doesn't actually affect whether or not this is an even function. Let's check that from the proof, from the actual definition. I can say f of minus x is cosine of 3 times minus x, which is cosine of minus 3x, which is plus cosine of 3x. So this is even. What about f of x is equal to x times cosine of x? Well, what happens to x when I change the sign of this? It's going to become minus x. So that's going to be an odd function. It's multiplying an even function, cosine. So that's going to give me odd times even. It's going to give me an odd function. Again, let's prove that from the definition. Just change the sign of x. I'm going to get minus x times cosine of minus x. That'll give me minus x cosine x, which is minus my original function. So this is odd. Last one, we've got f of x is equal to sine squared x. We've got sine squared x is sine x times sine x. These are two odd functions. So that'll be an even function. Again, let's prove that from the original definition. F of minus x, just replace x with minus x, so I get sine squared of minus x. So sine of minus x is minus sine x, but the whole thing is squared, which gives me sine of x squared, or sine squared x, which is my original function. So this is an even function. So these ideas are actually going to be very useful to us in this topic, because we're going to have to do a lot of different kinds of integrals over periodic functions. And if we can identify that these functions have some simple symmetries, it's going to make those integrations much easier. So let's see what I mean by that. The first one is to notice that the integral of an odd function between minus a and a is exactly 0. First of all, let me show you that graphically, and then I'll prove it. So we're going to use our classic example of an odd function. We're going to use sine. Let's get a little large, so let's get rid of that guy. Let's draw it a little smaller over here. So I've got, here's my function. Sine looks something like this. And let's say that we're integrating over this. So between some value, let's put a right here, and let's put minus a right here. So what would be the integral between minus a and a of this odd function? Well, I'm going to go between 0 and a. I'm going to get the area under the curve, and I'm going to go between minus a and 0, so I'm going to get the area under the curve, and these two areas are going to be the same, except they've got the opposite sign. So when I add them together, I'll get 0. So the proof is actually going to be very similar to this very simple intuitive idea. It's just going to be expressed in slightly more mathematical form. So I'm going to integrate from minus a to a of an odd function f of x, where I'm going to use the definition of an odd function, f of, so the definition of our odd function is that f of minus x is equal to minus f of x. Okay, so what I'm going to do here is I'm first of all going to notice that I can split my integral up into two pieces. I can have the integral from minus a to 0, and I can have the integral from 0 to a. So I can always do that with integrals. I can split up the integration from minus a to a into two pieces, minus a to 0 and 0 to a. Now let's focus on the first part here. So the integral from minus a to 0, I'm going to do a substitution. I'm going to introduce a new variable of integration. And that variable of integration is going to be x prime, we'll call it, which is equal to minus x. Now, what that does is it means that dx will become minus dx prime. The value of x at the limit integration at the bottom, when x is equal to a, will be a, and my limit of integration at the top will be minus 0 is 0. So my integration here is going to be replaced with the integral, so replacing the bottom limit of integration with plus a, top limit of integration with 0, f of, everywhere I see x, replace it with minus x prime, and dx is going to be minus dx prime. Now, the first thing I can do here is take that minus sign out, and the other thing I can do is actually swap the order of the integration here, swap a and 0, the limits of integration. And we know that when we do that, we change the sign. So I'm actually going to get two minus signs, one minus sign from here and one minus sign from swapping the limits of integration. So that'll give me the integral from 0 to a of f of minus x prime dx. Now we can use the fact that this is an odd function. So this is an odd function, so f of minus x is minus f of x prime, which is exactly minus of what's on the right-hand side of our integral above. The fact I've called it x prime rather than x doesn't change anything. So you can see that this expression here will be exactly minus this expression here, so these two things will be 0. So the integral from minus a to a of f of x dx equals to 0 for f of x is odd. So you can see that that's actually going to make life very nice when we're dealing with the integrals of odd functions, but only when the integral goes from minus to plus the same number, and that's an important restriction here. Let's take a look at what would happen if I had the integral of an even function between minus a and a. Again, what I'm going to do is I'm first of all going to sketch an example of what this would look like. In this case, I'm going to use the idea of a cosine. So cosine is our typical even function. Cosine looks something like that. And again, I'm going to imagine integrating this thing between minus a and plus a. And I'm going to do that by calculating the area under the curve. So calculate the area under the curve on the right-hand side, calculate the area under the curve on the left-hand side, and you can see that those two things are actually going to be the same. They're going to be the same and they'll have the same sign. So what I can do is I can replace my integral from minus a to a of an even function with twice the integral from 0 to a. That is, I've got two pieces that are the same. I could just replace it with twice the one on the right-hand side. So let's prove this again, and it's going to be a very similar proof. What I'm going to do is write my integral. First of all, note that we're dealing with an even function. Let's call it g of x, which is even, so g of minus x is g of x. And we have the integral from minus a to a of g of x dx. Again, we're going to write that as the sum of two pieces, one from minus a to 0, and one from 0 to a. We're going to use the same result that we had before for this expression here, because what we had up above just was a change of variable, right? It was an integration by substitution. So I can use that result in here to get the integral from 0 to a of g of minus x prime dx prime plus integral 0 to a g of x dx. So again, all I'm doing there is using the result that we had at this point here. Okay, so I know that this is an even function, which means that g of minus x prime is going to be g of x prime. So this thing looks exactly like the second term, except that x prime has been replaced with x. Those are just variables that we're integrating over, so this whole thing will be twice the integral from 0 to a of g of x dx. Okay, so let's put this to use. Let's take a look at an integral. So here I've got an integral x squared cosine 7x sine 2x over 1 plus x squared plus x to the fourth. It's a bit of a beast. But let's take a look at the symmetry properties of each piece in that integrand. This is equal to the integral from minus 3 to 3 of x squared. Well, that's an even function. If I replace x with minus x, I get the same function. That's multiplied by cosine 7x. Well, we know that's an even function. Multiplied by sine x, sine 2x, well, that's odd. And this whole thing is then divided by 1 plus x squared plus x to the fourth. 1, x squared, and x to the fourth, those are all even functions, right? Because if I replace x with minus x or x with minus x, I get the same thing back. So I'm dividing by an even function. So I've got even times odd divided by even. And division is just the same as multiplication when it comes to the properties of odd and even functions. So I have even times odd divided by even, so that whole thing will be the integral from minus 3 to 3 of an odd function. So I know that the integral from 0 to 3 will exactly cancel the integral from minus 3 to 0, so this thing has to be equals to 0. So I don't even need to do that integral, I just know from the symmetry of the functions involved that this integral has to be 0. Let's take a look at another example of a result involving even and odd functions. I'm going to prove that the derivative of an even function is an odd function. So let's introduce our odd and even functions. Let's say that g of x is equal to df dx, where f of x is an even function. So f of x has the property that f of minus x is equal to f of x. So let's set up an integral. Let's integrate from minus a to a of g of x dx. And I know from the fundamental theorem of calculus that that integral is going to be given by the value of f at the upper limit minus the value of f at the lower limit. So that's exactly the theorem of the fundamental theorem of calculus. But f is an even function, which means that f of minus a is going to be the same as f of a for all values of a. So this thing is equal to 0 for all values of a. Now, since this is true for all values of a, that means that g of x must be odd. Okay, so we've seen that odd and even functions are very important ideas, very useful ideas, especially when we're taking integrals of functions and periodic functions. So what we're going to do now is see how we can take a function which is not initially periodic, how we can make it periodic, and even how we can make it even or odd. So imagine we have a function that's defined in the following way. It's between 0 and 1, it's equals to 2t, and between 1 and 2, it's equal to 2. So first of all, let's sketch that piecewise continuous function. So this function is defined between 0 and 2. So here's 0, here's 1, here's 2. I know that the function increases linearly, like 2t between 0 and 1, and then it takes the constant value of 2 between 1 and 2. I know that I'm not including this point, and I am including this point, and I am including this point. So that is a sketch of what this function looks like. Now obviously this is not a periodic function, it's only defined between 0 and 2. But what we're going to do is we're going to turn this into a periodic function by using what's called the periodic extension. And all I mean by that is take this basic tile that I've drawn here and copy and paste it. Simply repeat it every 2 units. So let me put a little ring around my basic tile. This is the basic unit that we're going to repeat again and again in the periodic extension. So this is the function f of x. We're defining g of x, f of t, I think. Yeah, f of t. We're defining a function g of t, which we're calling the periodic extension. We're extending this function in a periodic way. It's the periodic extension of our little basic tile f of t. So let's start off again with our basic tile. Let's define between 0 and 2. And let's just repeat it all the way out to 4, 6, 8. So here's my original tile. It looks something like that. Let's now take that and repeat it again and again. Using the values of the discontinuities as well. And we're also going to do the same in the negative direction. Now notice that I have to be careful not to swap this around in any way. I'm just shifting it left or right. So it stays with the same orientation. It's just shifted by an amount 2 each time. So that gives me my function values, even for negative values of t. And you can see that that's going to be repeated again and again and again. So what's the period of this function now? Well, that's going to be given by the width of our original tile. So let's put a little box around that again. You can see that the width of this original tile is 2. So the period of this function is 2. Now I can use this idea of a periodic extension to calculate what is the value of my function, g, the periodic extension, at the value 8.3. And again, what I'm going to do here is I'm going to write this as a shift of 2 plus a shift of 2 plus a shift of 2 plus a shift of 2. Each of those shifts by 2, by 1 period, gives me back my original function. And I have a remainder of 0.3. So this thing is going to be given by g of 0.3, which is within our original boundary, our original interval 0 to 2. So I can go back and look at our original function, big F of, or little f of t. So that's the tile that I started off with. We saw that that was equal to 2t between 0 and 1. So it's going to be 2 times 0.3. It's going to be equals to 0.6. So that's how I can create the periodic extension of a function. I started with a function which wasn't periodic, and then I created a periodic function by simply copying and pasting that function again and again. And notice that I shifted it over by an amount 2, which was the width of our original tile. That tells me what the period of my function is. Now, this function doesn't have any particular symmetry. If I was to flip this left-right, or flip it left-right and up and down, it wouldn't give me back the same function. And we've seen that functions that have an even or an odd symmetry have nice properties when we're dealing with integrals. So what would be nice is to be able to create an odd or an even periodic extension. Now, the way that we're going to do that is by a two-step process. The first thing we're going to do is to take our original tile and double the size of it, so that we end up with a tile which itself is either even or odd. That is, even or odd with respect to swapping left and right. Then with this larger tile, which will be even or odd, we're going to again copy and paste so that we end up with a periodic function that's even or odd. Let me show you what I mean by that. So I'm going to define the even periodic extension, let's call it h of t. Even periodic extension of f of t. Once again, I'm going to start off with exactly the same original tile between 0 and 2. So that's a function that looked like this. And what I'm going to do is I'm going to double that tile, but in such a way that the new double-sized tile is symmetric. It's an even function. So remember what we mean by an even function. When I swap this thing in the left-right direction, I have to get the same thing. So let's take my tile and take its mirror image on the left-hand side. Okay? So notice that what I've done is I took my original tile, I took its mirror image, so I swapped the whole thing left-right to end up with a new tile, which is indeed an even function. The other thing that you notice is that this basic tile now has a width of 4, not of 2. It's twice as large. And that's going to be the period of my new function. Alright, so now that I've got my basic tile, I can copy and paste. So remember, I'm just picking this up and shifting it over. I'm not swapping it back and forth, and I'm not creating new tiles. I'm just picking it up and copying and pasting it again and again. So let's see what happens. I have this whole tile gets repeated. So not including that point, including that point, not including that point, and it gets repeated again. So I'm only going to fit in half a tile on this side. Likewise, we're going to do the same on the other side. And I'm going to pick that tile up and I'm going to drop it down. Pick it up, drop it down. So taking a look at this, you notice that this basic tile here is repeated again and again. And that the basic tile now has a width of t is equal to 14, t is equal to 4. So the period is equal to 4. This whole function now is both periodic and it's symmetric when I repeat left to right. So it's an even periodic extension. One thing you might notice here is that because I flipped left to right now, I have no value of my function at the points 2, 6, minus 2, minus 6, because the open circles now are lying on top of one another. So at this point, I'm actually free to choose what values I want to take for those values of my function. So I could, for example, put it down here or put it here. I suppose it makes the most sense to include the points there and there. So you can get sometimes a function which has no defined values at certain values of t, so you're free to choose what values are most convenient to you. Okay, so that's the even periodic extension of my function. What would the odd periodic extension of my function look like? Once again, what I'm going to do is create a basic tile that's twice as large as my original tile. And I'm going to do that by swapping taking a sort of a swapped version of my tile, or mirror image of my tile, in such a way that my new tile has got an odd symmetry. So I'm going to define a new function, j of t. This is going to be the odd periodic extension of f of t. Let's once again take my original tile between 0 and 2. So that's a function that looks like this. And I'm going to take that basic tile and double it in size by swapping it in the left-right direction. But I'm also going to swap it up-down, because we know that an odd function is one that's symmetric when I swap left to right and up-down. So I'm going to take my basic tile here, I'm going to swap it left right, and I'm going to swap it up down and see what I get. So that's going to give me something that looks like this. And here's my new basic tile. Once again, this is a tile that is twice as large as my original tile, which means that the period of my function is going to be 4. And once again, my basic tile has got a symmetry. When I swap this thing left to right and up to down, I get the same function. So this basic tile is now odd. And when I periodically extend this by copying and pasting, just picking it up, dropping it down, picking it up and dropping it down, I'm going to end up with a periodic function that is odd, the odd periodic extension of my original function. So let's see what that would look like. It's going to go like that. And then it repeats itself, and I'm only going to get a half a tile in for this one. And I'm going to do the same over here. And likewise, I'm only going to get a half a tile in over this side. So you can see that this is a repeating function. It's a function whose basic unit that's repeating, its basic tile, is odd. And so this whole function, when I swap it left to right and up down, I get the same function. It's an odd function, an odd periodic function. You also notice that, again, because the open circles here now are lying on top of one another, I don't actually have a defined value for my function at t is equal to 6 or 2 or minus 2 or minus 6. So I'm going to have to choose a value for this function, but I don't have the freedom that I had for an even function, because whatever I choose, it's got to repeat itself in an odd fashion. That it's got to have an odd symmetry. So when I shift left to right and up down, I have to get the same thing, and the only thing that that's going to work for is if I choose it equals to 0. You can play around yourself to see that that is indeed the case, but there's no other value that I can choose for my discontinuity that would be indeed give me an odd function.